Hi. Yes, it's free energy time. Oh, goodness. Normally I wouldn't touch these things. You've no doubt seen all these videos on YouTube of people, they've built up a circuit, a machine, whatever, and they're claiming free energy over Unity, and they're getting basically more power out than what they put in. They're against the laws of physics, they're bending the laws of physics, whatever they want to call it. Some people use quantum vacuum, blah, blah, blah. Doesn't matter what it is. They're all the same kind of fruity nut flavor. And, well, normally, yes, I wouldn't touch this sort of thing, but somebody mentioned it on the EEVblog forum. They pointed to a video, and not only that, but the author of the video actually came on the forum and tried to explain himself, explain what he was trying to do, and explain the circuit and how it works and all that sort of stuff. And yes, you pretty much guessed it, it got pretty darn hilarious. Link down below. So yeah, I think it's actually worthwhile taking a look at this thing. Now, normally it's trivial to debunk these kind of things, right? But I thought that actually this one is actually quite a valuable lesson in terms of how you can delude yourself into thinking that there might be something to this free energy. Or where does the energy come from? It looks like we're getting more energy out than what we put in. And of course, it always comes down to basic laws of physics, and in this case, some very basic engineering fundamentals that the people who build these circuits are not following. And so I think there's a few lessons to be learned here in what happens when you don't follow basic engineering principles and just assume that it's some ridiculous thing instead of it having a nice, simple engineering explanation. So let's take a look at it. Now, in this specific example, we'll take a look at a video from a YouTube user called Man of Stone 604, and I'll link it in down below. It's 5 minutes long, but if you want to save 5 minutes of your life, well, you know, it's up to you if you watch it. Anyway, he's made some various claims on this video and demonstrates a working circuit of how he can power 23 LEDs in parallel for 52 hours from a single AA battery. And no, I'm sure there's absolutely no trickery going on here. I'm sure the circuit he built up actually works, but he's giving the wrong reasons for why it works. He's not doing the basic engineering principles to see where the energy is coming from. So after we go through and sort of debunk and work out what's happening in the circuit, then we'll go on over to the bench, build it up, see if we can replicate it. So we'll go through the claims one by one and see how you don't even have to build the thing up to debunk this. It's really easy. So what he claims is that there's more energy out than in. That's in the title, the description of the video. The title of the video is Bending the Laws of Physics. So yeah, red flag right there. Now, as I said, power 23 parallel LEDs for 52 hours from a single AA alkaline battery. Okay, fair enough. Now, he also claims in the video, in the text, that each LED needs 20 milliamps for it to operate. Okay, that's your typical operating maximum operating current for a typical regular run-of-the-mill junk box LED, right? And he also claims that there's no coil in his circuit. We'll take a look at that. And he also claims, and this is very important, that the battery was depleted before he started the test. It was just some old junk bin battery he had from wherever, and crucially that he shorted it out for 1 whole minute as well. So he's claiming that it actually had less capacity than what it was supposed to. And on the forum, he started mentioning quantum vacuum and all that sort of stuff, and that he's been studying quantum vacuums for 16 years. So you think this would be a fantastic circuit, right? And whoa, this is 16 years worth of study has amounted to this. Oh, just wait and see. Now, to be fair, he doesn't claim he actually came up with this circuit. He's just doing a re-verification of what other YouTubers has done. And yeah, they're kind of a big circle jerk of free energy people who like to pat each other on the back. Anyway, this is the basic circuit here. I've redrawn it because it was really sort of confusing the way it was originally drawn in the video, but it's exactly the same. We've got a single AA alkaline battery here. Excuse the smallity of it. I wanted to leave it just over to one side, so we might draw it bigger later if we have to analyze it. But anyway, it's a 2-transistor circuit. It's got a capacitor and a resistor, and he claims no inductor. Okay, but so I've drawn it there as a wire and a bit of tube. And here is a shot of what he's got. He's basically got a bunch of toroids there, which he bought from DigiKey, and he gives the DigiKey part number. We can have a look at that with, he claims he's using Litz wire and all sorts of things going through, but basically he says it works with just a bit of copper going straight through the thing. So he's got one straight bit of wire going straight through some toroids. We'll look at that, and the LEDs just all in parallel. There's actually 23 of them in parallel across that coil there, and yes, it is a bloody coil. So that's the first thing. He claims there is no coil here, and he actually gives a value. He says that it has an AL value of 16 nanohenries. I'll explain that in a second. Well, for starters, he's got that completely wrong. It's 16 microhenries, not nanohenries. It's 16,000 nanohenries. Here's the data sheet. Look at the value of AL there. He's just got it completely wrong from the get-go. Basic engineering. Double check, read your data sheet. Now, he says he's using 3 of these DigiKey toroids here, as I said, sort of like stacked together like that. So I've only drawn one here, but there's actually 3 just pushed together like that. And he's basically got a single wire going through, and he claims that this is not an inductor. It's not a coil because there is no loop of wire. Oh, this is Inductors 101 stuff. You don't need to actually wrap the wire around the ferrite material for it to be a turn. When you've got a toroid like that, simply passing the wire through and looping with your circuit, because otherwise your circuit doesn't do anything unless you have a loop for the current to flow. You've got current flowing through there. That is one turn. One freaking turn, okay? It's a 1-turn coil. Now, I mentioned this characteristic AL of magnetic cores, like this toroid, and it's in the data sheet. Here is the value here, and it gives you a value it's an inductance value in this case, nanohenries, 17,600 nanohenries. As I said, he got he's out by 3 orders of magnitude there. And AL, what this value means, if you're using if the core's not saturated, you're using it in the linear region, for example, this is what the formula is. You can actually calculate the inductance. If you wind this thing yourself, you can actually calculate the inductance of that based on n squared times AL. AL is the value they give you in the data sheet for that magnetic material, and n squared is the number of turns. In this case, it's got 1 turn through it. If we actually wrapped it around the core like that, we'd have 2 turns, and so on and so on. So you can actually calculate the inductance. So we've got 1 turn, 1 squared times AL. We've got 17.6 microhenries for this 1 turn. But because he's got 3 core materials stacked like that, you actually add these 3 together. So you actually you work out the final value. Even with a single wire passing through like that, you still got in the order of 50 microhenries inductance. It's huge. That's a pretty decent size inductor for a switching oscillator like this. So that's just bullshit right there. That is done and dusted. He claims there is no coil. There is. It's a pretty damn decent one. You cannot debate this. It is not open for debate. It is basic 101 engineering. And if he actually had an LCR meter, he could go ahead and measure that, but he hasn't bothered to. Just jump into all these conclusions that it's free energy and can't even damn well measure an inductor. Goodness sake. Now let's take a look at the battery issue, the battery capacity. Now we've got a data sheet here for a typical alkaline AA battery from Energizer, fairly top of the range one, and it's got a nominal capacity of 2200 milliamp hours at 100 milliamps discharge. The capacity is going to change with the discharge current, but we're probably talking average, so that's not a bad value to actually take, and is pretty ballpark, in fact, probably about double ballpark to what we're talking about here. And then we have to look at the average voltage. So we look at the discharge curve there. I'm going to be a bit generous and say that the average voltage is around about 1.2 volts over that discharge curve there. So now we can calculate the capacity in the battery. We already have the capacity up here, but it's in milliamp hours. It's a bit better in this case when you're dealing with these sorts of things because you need power to power these LEDs. So it's better to actually talk about your total battery capacity in hours so that you can go, well, how much power are we consuming in our LEDs? Well, how much power capacity do we have in our battery? So in this case, we want it in watt hours. So we take our average voltage and multiply it by our capacity in milliamp hours, and that gives us around about 2.6 watt hours. And somewhat contrary to popular belief, the real, like the no-name kind of alkaline batteries you get out there aren't that far off the really good energized. In fact, some case they can meet or even exceed them. So you depending on what the discharge current actually is, because the characteristics change for, you know, there's little variations in the battery chemistry, all that sort of stuff. Anyway, for the ballpark engineering calculations we're doing here, we're going to say they're pretty darn well equivalent. And now for the very big, crucial claim in the video, right at the end of it. You've got to scroll through and there's some overlays on there. He says that he shorted the battery out for 1 solid minute. And he's implying there that, oh, that's sucking out a lot of capacity. Well, in engineering, we can calculate that. Once again, let's go back, look at the data sheet. Our internal resistance of our battery for a fresh cell, normally 150 to 300 milliohms. It's when you short out like this, it's probably going to be on the upper limit there. So let's take 300 milliohms there. That's our internal resistance of the battery. So when you short it out, it's the battery chemistry generating that voltage across the 300 milliohms there. So we'll take our average value there. We'll be a bit generous because if you short it out at the beginning of the battery life, well, it's going to be a bit higher. Anyway, let's work on our average voltage, be generous. So that is 4 amps. So 1.2 volts divided by 300 milliohms, that's 4 amps for 1 minute. And you think, oh, it's sucking 4 amps. That's a lot of capacity. Well, is it? Once again, we can calculate that. If you take that 4 amps, multiply it by our 1.2 volt average, that means that you are sucking out using 4.8 watts for 1 minute. Once again, sounds like a lot, but remember, it can deliver, this battery, 2.6 watts for a whole hour continuously. He's only done it for 1/60th of that. So let's divide that figure by 60 and we can find that it's used 80 milliwatt hours of our 2.6 watt hour capacity. It's bugger all. So you end up with the hilarious conclusion this guy has drawn that this is quantum energy, more energy out than what you put in. One of his main reasons for believing that is because he thinks that this battery had lost a very significant amount of its capacity, but we've shown that it's only around about 3% of its capacity. And yeah, he said like the battery was a year old. Whoop-de-doo, it might have lost another 5%. It's like we're down in the noise. It's still got most of its capacity left, even if you short it out for a full minute. This is basic engineering, and instead of jumping to conclusions that the energy must come from somewhere else and the laws of physics have been bent, no, just basic engineering. Look at the data sheet, read the values, do a couple of simple calculations, all using Ohm's law. Nothing more complicated than that. Oh, I think this is going to be a lot longer than I expected it to be. Anyway, hopefully people are learning something from this, including the guy who did the video. So look, we can scratch that one. Battery was depleted before start of the test. Yeah, it was, but not by any significant margin. And when you're doing something like this, especially when you're making extraordinary claims like, you know, the energy's coming from the quantum vacuum and you're bending the laws of physics. As Carl Sagan said, extraordinary claims require extraordinary evidence. But in this case, you didn't think, you know, to make these extraordinary claims to actually go in there and kind of do it scientifically and actually use a fresh battery. Instead, no, you whacked up a YouTube video. Oh, look, I think we've bent the laws of physics here because, well, I shorted out the battery and oh man. And now let's take a look at how much current the LEDs need to be bright. And in the video, he claims 20 milliamps. Later, he actually kind of admitted in the forum that, yeah, it's probably not 20 milliamps, but it's not 1 milliamp or less or something like that. Well, just look at the data sheet for a typical LED, and basically it's a linear relationship between intensity versus current. And well, you can define intensity various ways, but anyway, it's basically a linear relationship there, and LEDs are, even junk bin ones, are perfectly usable down at a milliamp or two, or even sub 1 milliamp. And modern high brightness ones, by modern I mean like the last 15 years or something, high brightness, high efficiency ones, well, they're usable down in the tens or hundreds of microamps range. So really, there's no reason to believe that your LEDs are being run at a high current. And of course, he didn't do the basic engineering. He hasn't measured the LED current. So once again, makes extraordinary claims, haven't even done some basic measurements like how much current is actually flowing through the LED. No, just thinks, oh yeah, 20 milliamps because, well, that's the maximum value of a typical LED. No! In fact, a lot of modern low power design relies on the fact that you can actually run only a milliamp or so through a LED, and you can get reasonable brightness in your product. So you don't have to piss away 20 milliamps. That's like theory from bloody 30 years ago. And the other thing too is because, well, this is clearly an oscillator circuit, it's going to oscillate. We're going to get pulses of current through the LED, just like pulse width modulating an LED, for example. I have no idea what the wave shape is going to be. Anyway, it's going to have an on-off time, something like that. So we're actually getting pulses of current through the LED. And you can actually get quite efficient performance of LEDs by actually pulsing them you can actually pulse them at 20 milliamps or even higher, but do it very briefly, even very briefly like that, and do it, once every 10 cycles or whatever. And you can actually get a decent apparent brightness out of your LEDs. So unless you actually measure that current, you don't know what it's working at. And as I've done a video on before, your amount of power you're actually consuming in your LED is basically the area under the curve. It's the integral like that. So you have to actually get, if it's a complex thing like this and it's not just a DC current, you have to actually, if you want the real power consumed in the LED, you have to get the scope shot of it and actually calculate the integral under the curve if you want to do really precise, proper, thorough engineering of this thing. But of course you can, you can just get your meter, of course, your current meter, and it'll just give you the average value over time for something like that. So that's, usually a reasonably solid result, getting the average value. But just be aware that it is actually the area under the curve there, the integral. And of course, that becomes more relevant when you've got like complex wave shapes, because we might have a complex wave shape in here. I don't know. We haven't actually measured it yet. And I don't know how long I've been yapping on for, but well, we could have skipped all that and just done some basic ballpark back of the envelope calculations to see if it's possible to light up 23 parallel LEDs for 52 hours from a AA battery. Well, we know a AA battery has got around about 2.2 watt hours or something like that. Well, look, at 23 LEDs, we know that we can operate a LED at 1 milliamp and actually get reasonable brightness out of it, as shown in the video, considering that he hasn't given any direct quantitative measurements of the brightness output. Well, we just have to match that. Okay, we know we can do that at like a milliamp or two. So let's just say a milliamp, 23 LEDs, that's 23 milliamps total. They operate at a slightly lower forward voltage at the lower current. You can see that on the curve. So around about 1.6 volts times 1 milliamp current is around 1.6 milliwatts to light up an LED at a similar sort of brightness to what's shown in the video. But we've got 23 of those, multiplied by 23, that's 37 milliwatts total. Milliwatts! And he actually shows a current meter coming from the battery actually in this thing, and it's a similar order. It's down in, like he's measuring, like I think it drops from 64 down to 18 milliamps or something like that. So at the battery voltage of 1.2, it's the power we're talking about, okay? And where does that power come from? Might come from a quantum vacuum free energy, woohoo! I don't know. Or does it come from the battery? Well, we know we've got 2.2 watt hours capacity in the battery there. 37 milliwatts here times the claimed 52 hours that he got, you know, working with average values here, it only comes out to 1.9 watt hours, completely within the bounds of the energy source you're using to power this circuit. So right there, you know that this thing, we can account for the power in these LEDs easily from the battery that we've hooked up to the damn thing. Oh my goodness, to make the jump to that it's, you know, Overunity or more power out than what you put in is just madness. Where's the evidence? There's none of it. So what have we got? We know that LEDs don't need 20 milliamps to operate. We do it all the time in engineering. Go do it yourself. It's a trivial 5-second experiment. And hey, we do know that we can actually power 23 parallel LEDs at a reasonable brightness for 52 hours from a single AA cell. Yeah, it's possible. No one's doubting that. I'm sure when we hook it up, we'll be able to measure these sorts of things, but you don't even have to. You can just do the calculations looking at the data sheets and know it's going to work. That's a great thing about engineering in science. All these things are proven. You know they're going to work. You can bet your life on it. Oh, and I also forgot one claim that, you know, he's using that as sort of evidence that, oh, this thing's drawing huge amounts of power, so it can't be coming, all of it can't be coming from the battery, in that the resistance through the core he's got here, he thinks it's just a core. Remember, he doesn't think it's inductor, but we know it damn well is an inductor. He says, well, the DC resistance through that core is 0. And, well, yeah, okay. He's right. Well, it's not 0, of course. It's pretty darn low. It's a really low value. But it doesn't matter. It's not working like that. It's an inductor. It's got quite a large amount of inductance. It's got like 50 odd microhenries. That's pretty huge in the scheme of things for a probably a high frequency oscillator like this one, based on the values of 47 PUF, and you know, it's going to be reasonably high frequency, hundreds of kilohertz or maybe even megahertz. So inductors don't work. When you've got an inductor, it doesn't work like that. You can't just say the resistance through the core is 0. It's just silly. You're not talking about the right thing. So let's take a very quick look at how this circuit works. And yes, I've just redrawn it over here, a little bit bigger so we can draw stuff on it, and we'll draw some waveforms here. Now, clearly this is an oscillator. How do you know? Well, it's got this classic 2-transistor relaxation oscillator arrangement with the feedback capacitor in here. Nothing fancy at all. A lot of people think it's like a Joule-Feith type variant. Well, Joule-Feith uses a transformer arrangement with the single transistor, kind of different. That you can get ones with just PNP, just NPN configurations. This one uses a PNP and an NPN. And by the way, the stated used transistor in there is a BDX33C. It's drawn as a single transistor. It's actually a Darlington pair, so it's got much higher gain than your regular transistor. We'll just chuck in a, you know, a 2N2222 or something like that. Going to be good enough for the job. So we've got a basic relaxation oscillator here. How do we actually start analyzing this? Well, for starters, when you first apply power, let's start looking for any DC paths to set these things up. Because we're using bipolar transistors, they're current-driven devices. You need current flowing in the base. If you've got current flowing into the base, then the transistor will turn on. So they're basically we're using these as on-off switches. They're not really being used in the linear way, hence the relaxation oscillator. Now, let's have a look at this. When we apply power, here's our 1.5 volt cell here. Okay, so we've got our 1.5 volts across here, and well, by the way, I haven't drawn in, that's ground. If you want to have your little ground symbol there, it doesn't matter. We've got our 1.5 volts applied across here. Well, let's have a look at our PNP transistor here. It's a classic BC557, and of course PNP, look, just follow the arrow. The current can flow through. Let's have a look. Can it flow down here when it's first powered up? Well, it can. Look, it's got this 100K resistor. It's got a current path down to there. So as soon as we apply the power, we can say that transistor is turned on. Okay, so we've got current flowing down here like this, and that transistor's turned on. So we're going to have current then flowing through the transistor down into the base, and this transistor down here is going to switch on because there's current flowing down through there like that. So when that transistor switches on, our current starts to flow through our inductor like this. The magnetic field starts to charge up in the inductor. That's how inductors work. Initially, it's going to try and resist the current flowing through there, but it's going to slowly build up. So the current in our inductor is going to start to rise something like this. We don't know what value it's going to rise up to. Doesn't matter. Now, we have to remember the key to this thing is this feedback capacitor here. It's only 47 puff, but remember that one's going to start charging up as well. And this voltage here, of course, is going to start going up as well, because as you increase the current, you're going to get a bigger voltage drop across your transistor here. So we'll draw that waveform as well here. This is this point here. The voltage is as the current rises through this inductor and hence through the transistor here, the voltage drop across the transistor is going to rise as well until it hits a point somewhere here whereby virtue of this feedback capacitor, the voltage on the base of this transistor over here is below the threshold voltage of the base emitter junction there, i.e., you know, your 0.7 volts or whatever it is. So it's going to rise up to about 0.7 volts below the battery voltage here, i.e., you know, it might be 0.5 volts or, you know, something like that. So it rises up to that point. What happens when this transistor no longer has enough base emitter voltage there? Well, it's going to switch off. What happens when that switches off or starts to switch off? It all happens very rapidly. So when this transistor here switches off, it deprives the base current of this main charging transistor down here. And what happens? Wham! It snaps off and bingo, we're now in a different state. And what happens at this point? Aha, here's the magic, okay? The voltage at this point is going to suddenly shoot right up. How far? Well, it depends on the collapsing magnetic field of this inductor here. So what happens at this point? Well, I've had to redraw this because our voltage now, once it reaches that threshold where this transistor switches off and this one switches off, bam, the voltage at this point is going to shoot up. Why is it going to shoot up? Because we've got a collapsing magnetic field in our inductor here. There's no longer any current flowing through it. So our voltage has to, it's like switching off a relay coil, for example. You're told to put a reverse diode across the relay coil. Why? When you switch off the coil, the collapsing magnetic field generates a large reverse voltage. So we've actually got a huge reverse voltage, positive, negative, like that. And what does that do? That swings the voltage at this point here up above our battery voltage here, which is sitting at our 1.2 volts average or whatever it is. Swings it up to a very large value at this particular point here. How large? Well, it's actually going to be clamped with our diode, because if you have a look, our diode is actually backwards. You know, if you thought about this conventionally and didn't know that this voltage here at this point went above the rail, then you would think that they've installed the diode back to front. Oh, no, they haven't. The reason it's back to front like that is just like a relay coil. It clamps that voltage across there, and hence, so when this thing collapses, voltage has gone up to this point, and we're going to have current flow now. Where's it going to go? The only place for it to go is through our diode and around like that. So we're going to have a huge spike of current in the diode like that. And of course, it's going to clamp it to basically the forward voltage of the diode. But you know, if we didn't have the diode here, then the voltage at this point could get very high, you know, tens of volts or whatever it happens to be. So we should actually be able to power pretty much any LED in here, regardless of its voltage drop, red, white, or whatever, even a series string of LEDs up to a certain voltage point. So I've drawn in the additional waveform here, or time correlated, for the current through the LED. It sits here during this charge cycle of the inductor. It does nothing. There's nothing, no current flowing through the lead, but when it goes wham and switches back and these transistors switch off and you get the collapsing magnetic field, bingo, your current shoots up through your LED, you get a huge spike. This could be like hundreds of milliamps. And here's one of the bad design aspects of this circuit. There's no current limiting LED, no current limiting resistor in this thing. So, you know, it's just going to wham, just put a voltage directly across an LED from a relatively low impedance source like this inductor. So you're going to get wham, huge spike of current, which is then going to ramp down like that. And it could be much above the rating of these LEDs. You know, they might have a maximum current rating, a continuous current rating of 20 milliamps, for example. A lot of them have a pulse current rating as well for a certain period of time, but you've got to be very careful not to exceed that sort of thing, can drastically limit the life of your LEDs. This is a really piss poor engineering solution. There's no current limiting resistor. You don't know, you know, the boundaries of your current conditions, and it's just, it's horrible. Right? But anyway, that's how it works. So it ramps back down like this. So the current through the inductor, of course, ramps back down, and of course the current through the LED ramps back down until you get, and the voltage at this point here will jump up to that higher voltage above the rail here, so it might be, I don't know, 2.2 or 2.5 volts or whatever it is, and it stays, you know, reasonably constant. And so at that point, it all starts again. Our current's going to ramp back up through there, and it'll basically, that should be some sort of sawtoothy type shape, and then bingo, this is going to happen again at some point, and it jumps back down to there, and then we're going to have another spike of current, and it oscillates at some you know, resonant frequency determined upon the capacitor and the inductor and a few parasitics and things in there. So that's how this basic thing is going to work. It's giving huge pulses of current, hence why it's probably reasonably quite bright, but they're going to be very quick and, you know, spaced apart by who knows what, depending on the time constants and stuff like that. So this is pretty much how it's going to operate. And of course the other piss poor thing with this circuit is that we've got all the LEDs here in parallel, and you just don't do that in professional designs because they're going to not evenly share the current like this. It's going to depend on the process matching of the particular dyes and everything else. It's just a horrible way to do it. It's just totally uncontrolled. But yeah, you know, it works for a hack circuit. So I think I've had enough of the whiteboard here. It's already debunked. You don't even need to build the thing up. And yeah, I'm sure it works. So let's go actually build this thing up. And yeah, I'm sure we can light 23 LEDs from a single AA battery, and let's measure the average current. We're not going to go into full-blown engineering mode and get in there and measure the integral of the curve. And you know, if you really wanted to do this extremely thoroughly to prove that, you know, scientifically that you've bent the laws of physics, or you're extracting energy from the vacuum, or you're doing whatever, then you'd want to be pretty darn sure about your precise measurements. You want to account for every single nitpicking picowatt in this thing. But yeah, so we're not going to do that, but let's power it up, have a play around with it. And because I have waffled on far too much in this video, this will be a very quick demo. Here it is. Ta-da! It works. Look at that. I'm powering it from 1.5 volts. I've got 23 parallel LEDs set up. No problems whatsoever. Here's my little Dave CAD drawing. This is the anti-bullshit edition. I've got a 2N3904 in there. That's a reasonable current general purpose ampere. We've got a BC 557 up there. I whacked in a 100 mic inductor. That's a little surface mount job down there. It's a bit higher than the 80 odd 88 I think we calculated from the 5 cores, but yeah, near enough. And exactly the same values, 47 puff feedback cap and 100k down to ground. And here it is. Check it out. No, there's nothing up my sleeve. And yeah, just a surface mount inductor, put on some leads there. I have my microcurrent actually in series with the LEDs up here, so that'd be up there. So, well, that'd be in that little link in there. So I'm actually measuring the current through the LEDs there. And what do we get? We get, sorry about the lights there, let's round that up to 12 millivolts, which is 12 milliamps, because it's I'm on the 1 millivolt per milliamp range there. So it's around about 12 odd milliamps taken from the LEDs continuously. And channel 1 here is actually powering the circuit. I've got it set to 1.5 volts, and it's currently drawing around about 24 milliamps or thereabouts, which is equivalent to about 36 milliwatts, which is less than half of what the guy got in his video, because he said he was measuring, as I showed, like 68 milliamps or something like that. So mine's, I don't know whether or not it's more efficient, but anyway, it's my particular circuit draws, my particular inductor and transistor. So anyway, we're proving the concept here. But as you can see, yeah, it's not drawing much at all. It's going to last forever. And if we go in here and we actually drop this voltage down, here we go, I'll tweak it down, 1.4 volts, as you can see, the current is going to drop, and the power, the total power that the circuit is consuming, that includes the LEDs and all the losses. And sorry, I should zoom out there. The LEDs, they're still on, okay? They're still on at 0.9 volts. And drop it down to, 0.8 volts there, and they're basically off. That's the threshold voltage of my particular circuit, which is exactly what you'd expect. And we're just probing a couple of waveforms here. Look, the oscillation frequency around about 91 kilohertz. So I was kind of in the ballpark of a couple of hundred kilohertz. We'd expect that to change with frequency as well. We might test that in a second. Anyway, the yellow waveform here is the one I drew on the board. And here it is side by side. And I said it had started at about half a volt and then work its way up. And does it? Well, here's the baseline down here, and we're at 500 millivolts per division. So yep, at about 1 division it starts to ramp up like that until we get to the threshold where this transistor can no longer conduct, and then bang, it switches that off, and then we get the sudden huge rise in voltage, which is then clamped by the LEDs in this thing. There's a bit of overshoot. Yeah, as you can see, a little bit of overshoot in there, but that's neither here nor there. There it is there. And as you can see, we've only got a 1.5 volt supply in this thing, right? But 500, 1 volt, 2 volts, 3 volts. So it's jumping up to around about 3 volts. That's not surprising. We've got our 1.5 volt supply plus our roughly 1.6 volt clamping voltage of our LEDs at the particular current. So yeah, there you go. That's what it's jumped up to. If we remove the LEDs, we would find that the voltage would jump up much higher. And I can do that by just disconnecting my current meter. There it is. And we'll have to go to 1 volt per division. Oh, wow, look at that. 2 volts per division, 5 volts, 5, 10, 15. Yeah, so it's really jumped up there to, you know, many tens of volts. And our blue waveform here, that is the base of our transistor there. So that shows the threshold voltage of the transistor plus the feedback via the capacitor there as well. And as you can see, that jumps up drastically once both transistors are off, because then it just, boom, it feeds straight back. So we do get a higher voltage here also than the supply voltage. And then you can see once the LED starts to discharge all the stored energy in the inductor there, it gets down to a point where there's no energy left in the inductor, and the voltage on the base here drops right back down, and bingo, this transistor switches back on, and then our ramp starts up again, and so on, and that's how it oscillates. And if we hook our scope up to the output of the microcurrent here, and we have to be very careful, we can't just keep our ground probes down here if our microcurrent is in here, because then we'll short out our ground references across there. So I've had to now take the scope ground from there. You can do it with differential inputs and other things, but anyway, I just moved the scope input up here, so the yellow waveform is still measuring the voltage here, but it's going to be a bit referenced a bit different. And then the blue waveform now is our LED current. You can see that those waveforms basically match exactly what we thought they would on the whiteboard there. So that's our LED current. It didn't rise up instantly, but it ramps down like that. And of course, there's no LED current for the period that the inductor is charging up. But when it dumps that magnetic field here, and all the current can reverse, the voltage reverses, goes above the rail and starts powering the LED, bang. So our LED is getting lots of little bursts of current like that. So overall, our circuits are actually pretty piss poor efficient. It's only about 50% or thereabouts, because as you saw, we've got a total average current of 24 milliamps there, and we're basically getting like half of that, 12 milliamps or so on average, going through the LEDs. So yeah, you know, not that great. Now, if you're wondering about these LEDs I'm using, well, they're about at least 20 years old. I think they're from the very early 90s, and they were basically the piss poorest LEDs I could find. I don't have a data sheet on, no idea what model they are, but yeah, I know for a fact that they're 20 plus years old, had them sitting on my junk bin. Now, I've put fixed exposure on this camera, so we know that there's a total of 12 milliamps flowing through these LEDs on average. So that means on the average current for each LED is only half a milliamp. Okay, half a milliamp, 500 microamps, and we're getting, you know, a reasonable brightness here. So I've got fixed exposure. I've got the same LED over here, and as you can see, that one, well, I'll show you that at the same time. That one is exactly the same LED, but I've got that at a fixed current of 20 milliamps. So that's basically the maximum current. And it's not a huge amount brighter. If I go in here, okay, and let's adjust the current. There we go, 19 milliamps, 18, 17, goes down. See, and we get down to, well, 0, so I don't know. I'd have to actually get in there with a meter and measure it. But if it's like 1 milliamp, for example, no, that's 2, 1 milliamp. It's basically a little bit brighter than what we've got here. So once again, fixed exposure. I'll try and show you that. That's at 20 milliamps now. So I'll wind that down. 18, 16, 15, 8 milliamps, 5 milliamps. And as you can see, that's down at now 1 milliamp or thereabouts. As you can see, it's pretty similar brightness to those. So yeah, it looks like they really are running at the claimed average current, or the measured average current, as you'd expect. So yeah, these suckers are running at half a milliamp average. There you go. No problems whatsoever. And then just do the math on a current draw, an average current draw of 24 milliamps or 36 milliwatts from those batteries. This will last even much longer than the 52 hours the other guy got. So no problems whatsoever. There's no magic core freaking happening here. I'm just using an off-the-shelf Joe Bloggs SMD bloody inductor in there of 100 microamps. No worries, I can power 23 LEDs, the piss poorest LEDs I could find. They're absolutely horrible. Even at 20 milliamps, the damn things are absolutely useless. There it is at 20 milliamps. That's how bright they are. They're hopeless LEDs, and it's fine. So, geez, no wonder he got this thing working. And there's no magic happening. There's no quantum vacuum. There's no bullshit. It's just basic engineering. It works. So there you go. I hope you enjoy that. I know it's been a lot longer than I anticipated, but hopefully there's a lot of information in there and some people learnt something anyway. And yeah, there's no magic to this. We aren't bending the laws of physics. There's no quantum vacuum. We're just doing basic, real engineering here. It's very simple if you don't have that unwavering belief that you're getting, you know, energy out of a quantum vacuum or whatever it is you think you're getting, this free energy or over unity or more energy out than what you're putting in. If you go through and do the measurements and the calculations properly, and they're not hard, and we haven't done the full suite of, you know, working out where accounting for every little bit of energy, but no problem. We can light the 23 LEDs with, you know, easily for the amount of time this guy claims, and it's not a problem at all, and they're the worst LEDs in history. Unbelievable. So this is what happens when you believe stuff instead of actually doing the engineering, using the scientific method and actually thinking about this sort of stuff. Free energy is just busted. It really is. It's bullshit. So yeah, please, if you're going to do this sort of thing, at least do the basic measurements and understand what you're doing. So there you have it. Oh, this belief in free energy, quantum vacuum, whatever you want to call it, is just wishful thinking of biblical proportions. It's just ridiculous. And unfortunately, we probably won't change a lot of these people's minds because this is what they deeply believe. And as he said, he spent 16 years researching this and studying it. And, well, you know, it's probably not easy for them to give up because they've got such a deeply held belief. No matter how much evidence you throw at them, that they've got it, like, completely wrong. Like, for circuits like this, it's bloody obvious where the energy comes from. It comes from this thing, the battery. In this case, power supply, but the battery, you hook up to it. I mean, God, how can you not see that? Oh, it's like facepalm worthy. It really is. It's so bleeding obvious. Anyway, I hope they've learnt something from this anyway, that these circuits that they're working on are just basic engineering. There's nothing magic whatsoever. So anyway, if you liked the video, jump on over to the EEVblog forum. Link is down below as always. And if you like the video, please give it a big thumbs up because that always helps a lot on YouTube. And follow me on Twitter and all that sort of stuff. And if you like the shirt, there it is. You can always buy it on my merchandise page down below. Catch you next time.